Let us start with surface tension today. Surface tension is basically the force per unit length acting on an interface. So basically this deals with surfaces or interfaces. Generally, the small elements we consider are only a few molecules in width. So what we're talking about is things on a very small scale. However, this effect can be integrated over a large area to help in our calculations. This is generally observed prominently in liquids, which will be our main area or topic of discussion in the later class. Before we go into great detail, let us bring up something from the very chemistry what we learn. The chemistry of atoms, or what you generally study in the atomic structure, which is the forces between two atoms or a group of atoms. Let's consider this graph. This graph is between potential energy and the distance of separation between two atoms. Experimentally, it was found that this graph looks something of this form. This is an asymptote, or a line which meets this curve at infinity. This r-axis is basically the asymptote. This point on the r-axis, say, is r0. So what we see is when we come down from the potential energy axis towards this side, we see that potential energy decreases from a positive value as the separation is increased, comes to a 0 here, keeps on decreasing to a negative value and achieves a minima or a point of minimum here, which is at a value of r0. As we go beyond this, it again keeps on increasing from a negative value, still being negative, till it reaches 0 at infinite r, or infinite distance of separation. Now, what happens is anything on the universe, or let's say our planet Earth, tries to attain a state of minimum energy. We cannot have a situation when an object or a body or anything is stable under a very high energy configuration. So whatever we see, whatever we look at, basically everything is trying to attain a very low energy state. Same thing goes with atoms. Here, the atom, the distance between two atoms is optimum at r0, which is the potential energy created between them is at a minimum. So all molecules tend to attain a distance of r0 between them. All molecules tend to attain a distance of r0 for equilibrium or low energy states. So what happens here till r0, let's talk about this part of the graph. This part of the graph experimentally shows that there is a net repulsion between two atoms. This part of the graph, which remains, gives us an idea of the attractions between two atoms. This concept of attractions and repulsions between atoms can be extended up to molecules also. Because there are net forces between these two molecules or atoms, these repulsions or attractions come into the picture. So, there is going to be a net force on the molecule. This is the basic or the physical aspect of this topic. Let us consider a more practical aspect of the same topic.